Let us try to derive the magnetic flux density due to a long thin solenoid. Now we can use Ampere circuit law if we know something about the magnetic flux density or we have some kind of symmetry. So a solenoid is usually made of wires wound closely. So let us say these are wires which are wound closely. So current will be exiting from one end and entering in another end. So let us say it is dot in all these conductors, that is current is leaving out of the plane of the paper and entering the plane of the paper in this portion. Now experimentally it is found that the magnetic flux density is nearly zero outside this solenoid and its value is only high inside this solenoid. Now we have this information that the flux density is there only inside it and outside it is very near to zero, and also we know that divergence of this is equal to zero. So it means that inside the solenoid the divergence should be zero and it should exist, so it means that it should be parallel to the axis of the solenoid. So you see that from a simple information that the flux density is zero outside and uniform inside, we have found the direction also just by using this divergence of the magnetic flux density. So in this way we have found the required symmetric condition. Now what we will do, we will take this solenoid and again we will make a Ampere's circuital curve. Let us say its length is L, its height is H. So we will calculate B dot dl along this curve. So here B will be B AX, and we know that B is only BAX. Here it is 0 and here it is also 0 and here in the direction. So let us say this is X direction and this is Y direction. So the only term surviving from this whole thing is B into L, because for this curve it will be perpendicular, dl will be perpendicular to b, so it will be 0. Here already b is 0, so it will be 0, so it will be 0 because b is 0. Here b is 0, that's why it will be 0, and here dl and b are perpendicular, so it is 0. So only contribution will be from this. So this will be equal to the total current enclosed. So let us say there are n turns per unit length of the solenoid. That is, let us say there are total number of turns is L n and total length is L. So this will be this thing. So for our case the enclosed current will be B is equal to mu naught n into L I enclosed. Let us say this is small l, so that the total length is L and this curve length is small l. So B will be mu naught ni and the direction will be in AX direction, that is in this direction. So in this way we have found the magnetic flux density due to a long thin solenoid and also the direction we have found. Now this is the number of turns per unit length. This is a constant for a given solenoid. So you see that the magnetic flux density inside a solenoid is a constant for a given current in the conductors. Now, what will happen in at the ends of the solenoid? So, at the ends of the solenoid, we know that these field lines cannot just terminate themselves. They should terminate towards each other. Means they should close on to themselves because there are no magnetic monopoles. So they should somehow diverge and meet their endpoints. So these field lines are pretty similar. Now here density is very high, inside the density is very high, and outside this density is very low. So the field is nearly zero outside and constant inside. So these field lines resemble pretty closely to that of a bar magnet. So that's why whenever we require a constant magnetic field similar to a bar magnet, we can use a solenoid to create this kind of magnetic field. And that's why we use solenoids for electromagnets. Now these magnets are usually made of iron, so this gives us a hint that iron should also be having some kind of circulating currents in them to create the magnetic field. So classical theory says that the iron atoms have electrons which have their spins, and I think per atom there are two electrons available with this spin aligned with them. So since there are so many billions of atoms in a small portion, so all those collectively, those all electrons spinning create a magnetic field similar to that of a solenoid. So in this way, by classical theory, we explain magnetism uh, in the permanent magnets. Although we will study something in detail in one of our future lectures about them. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.